Hey everybody, welcome back to chemistry class. Today we're going to be focusing on rate of reaction. Now, when you see the word rate, we should think about time, and we are measuring the time it takes for reactions to take place. Now, in some books, you'll see how fast or slow a reaction takes place. There are some reactions that are extremely very slow, like, for example, the roasting of iron takes place over a few days, and there are a few weeks or months. Iron rusts over time, like a long time. No, there are some reactions that are instantaneous. They happen immediately. For example, we have reacting acid with carbonate. Those reactions are very immediate. There are other reactions that needs energy for them to take place. We need to heat them. We need to apply pressure and so on and so forth. No, CXC defines. So today we want to look on rates of reaction, and we are going to be looking on, one second. We're going to be looking on, let me change the slide here. All right, so today we want to define the term rates of reaction. We want to state the collision theory. We want to describe how the rate of reaction is measured. We want to interpret graph of rate of reaction. And we want to state factors that affect the rate of reaction and explain how each factor increases the rate of reaction. So that's what we're going to do today. Now, the rate of reaction is a change in the concentration of reactants or product per unit time. So for time, we can measure time in seconds, or we can measure time in minutes. So it's the change in concentration of reactants or product per unit time. Now, there are various things that we can, so we know that the concentration of a reactant, so we know in a reaction, reactants are converted to products. And we know that in a reaction, the concentration of our reactants are going to decrease. So the concentration is going to be decreased. That is because our reactants are being used up, and the concentration of our products are going to be increasing. That is because products are forming. So we will have a buildup of product and a decrease in the amount of reactants available. Now, we know reactions occur because there are various signs that we see in a reaction, right? So signs that tells us that a reaction is occurring are going to be change in temperature. So we spoke about this when we did endothermic and exothermic reaction. That for some reaction, we can have an increasing temperature, and for other reactions, we can have a decrease in temperature. Now, we also have formation of precipitate. So we're going to be doing a SVA lab where we're going to be having formation of precipitate. So we're going to use how quickly the precipitate form to determine the rates of reaction. Effervescent. So when we react carbonates and some metals with acid or carbonates with acid, a gas is produced. So production of effervescent shows that reactions are taking place. Signs of chemical reactions are we have color change. So in our lab, we can manipulate any of these. We can time how fast it takes for the color change to occur, how fast a precipitate occur. We can measure the change in temperature of a reaction, how fast or slow this temperature change occurs for us to get the rates of reaction. Or we can just measure the change in concentration of reactants or the change in concentration of products, right? No production of light. So for example, we have bright light forming or light decreasing. That is a sign of reaction proceeding. Now we are into the collision theory. This is a very, very important for us to understand the rate of reaction and the factors that affects the rate of reaction. Now, in order for a reaction to occur, the reactant molecule must collide, but is not any collision is going to produce a reaction. The molecules that are colliding must collide with the proper orientation. So they must hit each other at a particular angle for the reaction to occur. And these reactants must have enough energy in order for the reaction to occur. So these two things, and with enough energy, we call this the activation energy. activation energy is the minimum energy a reactant need in order to collide and form products. All right, so they must collide with the correct orientation. So as a result, only a small fraction of collision meets these requirements. So it is not every collision that is going to be successful or effective to convert reactants to product. In order for us to get reactants to form to product, they must collide, reactants must collide at the proper orientation, the correct angle, and they must have enough energy. They must have their activation energy, which is the minimum amount of energy the reactants need in order to collide to form products. So once we understand this, we will understand what is happening in a reaction. Now, understanding a reaction. At the beginning of the reaction, I have a high concentration of particles of reactants present. There's a high concentration of reactants, right? So what is happening is when I carry out a reaction in the beginning of the reaction, the only particles that are present are particles of the reactant. No product has formed. So the only particles I am seeing is the particles of the reactant. And so the reactants are in high concentration. So the reactant particles are in high concentration. And because the reactant particles are in high concentration, we have a lot of collision taking place. But remember, not all collision will be successful. In order for us to have successful collision, or effective collision, they must collide at the correct orientation and they must have the minimum amount of energy. So we have more collision taking place. So if we have a lot of collision taking place at the beginning of the reaction, therefore we're going to have more successful collision, and so the rate of reaction is highest. So at the beginning of all reaction, we have a high concentration of reactants. So the reactants are in high concentration. So we have a lot of collision taking place. So if we have a lot of collision taking place, we're going to have a higher chance of successful collision. And so the rate of reaction is highest in the beginning of the chemical reaction. Now, as the reaction proceeds, or reactants are going ahead to form products. So we're going to have less reactant particles available and more particles of products present. So when these particles are colliding on a molecular level, we can have reactants heating up into products. We can have different types of products too. So we will not have as much successful collision as we had in the beginning. So as the reaction proceeds, less reactant particles are available. So we will have less successful collision. This is because some of the reactant, so we have less reactant particle, more product particles forming. And so the chances of reactant to collide with reactants at the right orientation with the sufficient energy is going to decrease. So if that probability decreases, what we're going to have is less successful collision. And if we have less successful collision, the rate of reaction is going to slow down. Let's go again. When reaction starts, particles are in high concentration, so they collide a lot. Reactant particles are there. So they're going to collide a lot. Because they're colliding a lot, the chances of successful collision is high. So the rate of reaction is fastest. Now, as time progresses, what is happening is our reactants are being used up and products are forming. So not all of these collisions are going to be successful. That is at the right orientation with the right amount of energy. So the chances of having less successful collision becomes less. So because the chances is less, the rate of reaction slows down until eventually we are going to use up one of the reactant known as the limiting reagent, and when that happens, the reaction will stop. So when one or more of the reactants are used up, there are no more reactant to collide to form product, so the reaction is going to stop. So let us understand this in terms of a popular reaction. So we can react marble chip, which is calcium carbonate, with hydrochloric acid. Let me go ahead in my state symbol. So calcium carbonate is also called marble chip. We need to know that because sometimes they refer to it as that in the exam. So calcium carbonate reacts with hydrochloric acid, which is aqueous, 2 moles of hydrochloric acid to produce calcium chloride, aqueous, carbon dioxide gas, water liquid. So in this reaction, we have a solid here. The solid is going to decrease. So another sign of this reaction is as this reaction proceeds, the mass of the calcium carbonate is going to get less. So it's a solid. So it's reacting with HCl, so it is going to become less. When it becomes less, we can measure the rate of reaction by the decrease in mass of the calcium carbonate, because the mass of it is getting less over time. It's a reactant, so it's being used up. Or carbon dioxide is a gas. We can measure the gas in a syringe and measure the concentration of the gas. So in this reaction, in the next slide, we're going to be looking on how do we measure calcium carbonate and what kind of information can we get from this reaction. So let us clear the screen. Here we have calcium carbonate here reacting with hydrochloric acid. So it's reacting. As it reacts, the gas, which is carbon dioxide, is going to go, this is a stopper, syringe, and the reaction is taking place in a conical flask. Should be able to label this. All right. So as the carbon dioxide evolves, it is going into the gas syringe. Over time, we can record the volume of syringe, let us say every 10 seconds, or every 20 seconds, or every 30 seconds, or every minute. So we're timing, every time we're going to choose a time interval and record the volume of carbon dioxide that is collected. So at the end of the day, we can plot a graph of volume of carbon dioxide collected versus the time. Clear? And what we're saying, what this slide explains to us, is that we are going to realize that the reaction, when the rate of reaction is fastest, time is less. So rate of reaction, if the rate of reaction is fast, it means we have less time to form product, right? Products are formed in a quick time. When rate of reaction is slow, products are formed in a very slow time. So we had explained that in terms of the shape, in terms of what is happening in a reaction. So we're going to look at how this graph that we're saying, the volume of carbon dioxide plotted against time will look. So here, we are going to realize that our graph is steepest at the beginning of the experiment. The graph is steepest. This is because the rate of reaction is fastest. So here, we'll go back to our explanation for 1. Rate of reaction is fastest. This is because at the beginning of the reaction, we have a high concentration. Let's go back. At the beginning of the reaction, we have a high concentration of particles of reactants present. So we'll have more collision taking place, therefore more successful collision. So rate of reaction is highest. Over time, when we are going to realize that our graph is no longer steep. So our graph is becoming less steep. This is because, so here, our reaction is going down. We know this because of the amount of time it is taking for us to get some product. So our graph is no longer steep. So to form this amount of product, this is the amount of time it takes. To form this amount of product, this is the time it takes. So it takes more time to form a smaller volume of gas. So we realize the reaction is slowing down. This is because concentration at this section is our explanation at 2. Concentration of reactant decreases, therefore, less successful collision or effective collision. So the rate of reaction is going to be less. Once we have less successful collision, rate of reaction, the reaction is slowing down. Once we have a lot of successful collision, the rate of reaction is highest, right? And then here we are seeing that the final volume of gas which is produced ends here, right? So here we have a flat section. There is no slope here. This means the reaction has ended. And so that means the limiting reagent has been used up, so we can have no more effective collision. So the reaction stops. So 1, here the graph is steepest. So we use the explanation for 1 here. What happens during a reaction? Reaction concentration of reactants is high. So we're going to have a lot of collision between reactant particles. If we have a lot of collision, then the rate of the chances of having successful collision is highest. So the rate of reaction fastest there. Over time, our reaction vessel will have products as well as reactants. So the concentration of reactant has decreased. So we're going to have less collision between our reactant particles, right? So if we have less collision, that means we're going to have less successful collision. So the rate of reaction slows down. And our reaction ends when one of the reactants or both of the reactants have been used up. So there are no more particles to collide, and so we cannot get any more products. All right, let's look on this reaction here. So we can measure the change in mass of a reaction. If we do that with time, we're going to realize that the mass of the reaction vessel is going to decrease. It's decreasing because carbon dioxide is allowed to leave. So the mass of it is going to get less. As carbon dioxide is formed, it's going to diffuse through the filter paper. And so our reaction vessel is going to get less. So we can measure this rate of reaction. When we do that, right? So there's 2 ways, and you're asking TXT questions to draw these experiments, right? There are 2 ways in which to do it. You can either measure the volume of carbon dioxide, which you just talk about, or talk about the decrease in the marble chip or the decrease in mass of the reactant. So the mass of calcium carbonate is going to decrease because it's using up. So of course, here we have a lot of calcium carbonate. The decrease is a lot, whereas here, the decrease is not so much. So at the beginning of the reaction, the graph is steepest because 1, high concentration of reactant. So if we have a high concentration of reactant, we have a large amount of collision. So if we have high collision rate, therefore we will have a lot of successful collision. So rate of reaction is high. When we get to this section of the graph here, the reactants are being used up. And products form. So less collision is occurring between reactant. So if we have less collision occurring, that means less successful collision. Slower rate of reaction. Here, this horizontal section here means reaction stops. One reactant is used up. Therefore, no collision. So the reaction, no collision between reactants. So the reaction ends. All right, so that's what's happening there. Now, there are certain factors that can affect the rate of reaction. So remember, you affect the rate of reaction by slowing. So these things will slow down collision. So if collision is slowing down, that means we have a decrease in rate of reaction. Or if we can increase collision, we have a high rate of reaction. All right, so these are some factors that can affect the rate of reaction. They can either slow it down or speed it up, right? But we're going to talk about increasing the rate of reaction. So we have concentration, temperature, surface area catalyst, and pressure. We're going to discuss them in no particular order to see their effect on rate of reaction. So we're thinking about how we can speed up the rate of reaction. So in the next slide, we're going to talk about the effect of concentration in speeding up the rate of reaction, how changing temperature speeds up the rate of reaction, how changing surface area speeds up the rate of reaction, and how adding a catalyst speeds up the rate of reaction. So we're talking about how to increase the rate of reaction. No, the first one we want to look at is increasing the concentration of the reactant. So what increasing concentration of reactants does is what it's doing is giving more reactant particles. So more particles are present in the volume. So if we have more reactant particles, they are going to collide more frequently. So increasing the concentration gives us more reactant particles. So if we have more reactant particles, they are going to collide more frequently. This results in more successful collision, and so the rate of reaction is fastest, right? Now, increasing the temperature. Increasing the temperature does two things. Firstly, it gives the particles, it gives more particles the activation energy. Remember we said in order to collide, the particles must have the activation energy or the minimum amount of energy, right? So when we increase the temperature, a lot more particles have the minimum amount of energy. So more particles are able to collide, right? So they collide more frequently, resulting in more successful collision, and the rate of reaction increases. Also, increasing the temperature gives the particles more energy. Once the particles have more energy, they're going to move around faster. So they will have more energy. So they will move around faster. So if they're moving around faster, they will collide more frequently. And this will result in more successful collision. And so the rate of reaction is faster. Adding a catalyst. Adding a catalyst lowers the activation energy. So that means this minimum amount of energy is going to become lower. So more particles will have the minimum amount of energy required. So if more particles have the minimum amount of energy, when they collide, they're going to collide more frequently. This results in more successful collision, and so the rate of reaction is fastest. Or for gases, we can increase the pressure. When we increase the pressure, we are decreasing the volume. So we are making the space that the reactants particles are less. So the particles are now in a smaller space. If the particles are in a smaller spaces, they're going to collide more frequently. And so it's a small amount of them in a tiny space. So they're colliding more frequently. So this results in more successful collision, and so the rate of reaction is fastest. We can increase the surface area. So for example, if we have a potato and I'll put the potato whole in the pot to boil, it's going to take a long time for the whole potato to boil. This is because only a certain amount of the potato particles are exposed to the temperature, right? To cook the potato. But if we want our potato to cook faster, we are going to dice up our potato. When we dice up the potato, we are exposing way more potato particles to the heat so it can be cooked. So increasing the surface area exposes more particles. So in the lab, we are moving from granules, which are big particles, to powder. So increasing the particle surface area, we're going to use the powdered form. Using the powdered form, more particles are exposed. More of the particles are exposed. And the more particles we have exposed, that means we have more, they will collide more frequently. This results in more successful collision or effective collision, and so the rate of reaction is faster. Clear? No, the reverse is going to be true. If we decrease the concentration, what is happening is we'll have less particles per volume, they'll collide less. This results in less successful collision, and so the rate of reaction is fastest. So the opposite is true. So once to memorize what's happening in the forward direction where we increase the rate of reaction, if we do the opposite, the rate of reaction is going to get less. Now, here we are going to look back on our reaction with we're going to be looking back on our reaction with the formation of carbon dioxide. Now, we can speed up the rate of this reaction. If we speed up the rate of this reaction, it means that our reaction is going to happen faster and we're going to form the same amount of products in less time. Clear? So the reaction ends here in a faster time than it ends here. So in red, this means in order to increase the reaction, the rate of reaction, I can increase concentration of HCl, right? Or use powdered calcium carbonate, right? Or increase the temperature of the reaction. So the temperature I'm carrying out the reaction, I can add to the temperature of the reaction, or I can add a catalyst. I wouldn't use the pressure here because pressure will only do that when we're reacting gases. There are no gases reacting. So on an exam question, they can give you graph and say to you, this is a graph showing the production of carbon dioxide. On this graph, sketch a new curve which shows the effect of increasing temperature using a powdered version of calcium carbonate or increasing the concentration of HCl or adding a catalyst. How will this affect the rate of reaction? Now, in my green ink, I am going to slow down the rate of reaction. So in slowing down the rate of reaction, I am going to be forming less product over time. And it will take a longer time for my reaction to end. So my reaction would end here normally, but I can slow it down so it takes a longer time to react for it to react. Now in doing this, I can decrease concentration of HCl, use lumps of calcium carbonate. So I'm exposing less surface area. I can decrease the temperature, have the reaction occurring at a colder temperature, or do not use a catalyst. So we wouldn't add a catalyst. So these are the three things that can slow down the rate of reaction. Clear? Now, here we have the other graph. On the other graph, in red, I'm going to put the conditions to speed up the rate of reaction. And in green, I'm going to show you how the slope of the graph is going, how the graph changes when I slow down the rate of reaction. So in red, if I want the reaction to occur faster, I need to end this reaction in a quicker time. So the time the reaction takes to end is here. I want to end the reaction at a quicker time, so I want the reaction to end here. So in order to make the graph steepest, I'm going to increase concentration of HCl, use powdered calcium carbonate, or increase the temperature of the reaction. Or if I want to slow down the rate of the reaction, I want the reaction to take place much slower. I want to make the reaction take a longer time to end. So I am going to decrease the temperature or the concentration of HCl, or I can use lumps of calcium carbonate. So that's it for rate of reaction. I hope you're able to understand it. The next time we meet, we are going to be doing an experiment measuring the rate of reaction. Thank you so much for watching. Please remember to like, share, and subscribe to my channel. Share the video with a friend.